Hello students, and in this video we're going to go over some basic information from chapter 8. And since we're going to skip section 8.1, we're also going to cover some basic information from section 8.2. And if there's any time left over in the video, we'll cover one example from the homework in section 8.2. So let's go ahead and get started. So chapter 8 is about hypothesis tests with two samples. Okay, so in the previous chapter, we looked at hypothesis testing with one sample. So you may remember that we performed hypothesis tests on the mean, proportion, and standard deviation of a population. In this chapter, we will perform hypothesis tests with two samples where each sample comes from a different population. So we will skip section 8.1 like I mentioned earlier. So in section 8.2, we will perform hypothesis tests on the difference between two population means, where the two samples are independent. In section 8.3, we will perform hypothesis tests on the difference between two population means using two samples that are dependent. So in just a few minutes, we'll describe the difference between independent samples and dependent samples. And then lastly, in section 8.4, we will perform hypothesis tests on the difference between two proportions. So in other words, in this chapter, we focus on two population parameters, right? Whether it's two means with independent samples or two means with dependent samples, right? Or two proportions. Keep in mind that there are two populations and we're collecting a sample from each of the two populations when we do the hypothesis tests in this section, although we won't collect any data on our own. Okay, so next, when we perform hypothesis tests on the difference between two means, okay, it is important to know whether the two samples are independent and dependent. So in other words, independent and dependent are keywords from your book, okay, in section 9.1. All right, so the two samples are said to be independent if the individuals in one sample do not determine the individuals that are selected in the other sample. Okay, so in other words, there is no relationship between the individuals in two samples when those samples are independent. So in other words, I've just given you a definition of what it means for two samples to be independent. Okay, and you can check the definition I have here with the definition given in the book. Okay, so it captures the main points of the definition of the book. Okay, so two samples are dependent if the individuals in the first sample determine the individuals that are selected in the second sample. So in other words, there is a relationship that connects the individuals in the first sample with the individuals in the second sample, okay, when the samples are dependent. Okay, and we'll go ahead and look at some examples, or an example of an independent sample and an example of a dependent sample so you can see the difference between the two samples. So when the two samples are independent, okay, their sample sizes are usually different. Okay, but in some cases, right, when you have independent samples, right, the two samples may contain the same number of individuals. So in other words, their samples may be the same size, but that's not always the case. So for independent samples, okay, their sample sizes are usually different. Okay, but when the two samples are dependent, their sample sizes should always be the same. Okay, so you're not likely to see two dependent samples, okay, where one sample size is different from the other sample size. So in other words, with dependent samples, their sample sizes should always be the same. Okay, that's usually one way you can tell that you're dealing with two samples that are dependent, right? If their samples are the same size. However, you do want to read the problem carefully to determine whether the samples really are dependent or independent. Okay, so let's discuss some examples, or an example of an independent sample, and then an example of a dependent sample. Okay, so some examples of dependent samples are husband-wife data or before and after data on the same individual. Okay, so once you understand what it means for a sample to be dependent, okay, then you'll automatically understand when two samples are independent. Okay, so again, husband-wife data or before and after data are two common examples of two samples that are dependent. Okay, so for example, we may want to know whether husbands are generally taller than their wives. Okay, so in other words, I'm going to describe two situations, right, where you have two samples that are dependent. Okay, so to collect the appropriate data, we would randomly select married couples from the population and then measure their heights. Because remember, we want to know whether husbands are generally taller than their wives. So one sample would contain the husband's heights, while the other would contain the wives' heights. Okay. So then why would these samples be dependent? Okay. Well, the two samples are dependent because each husband is paired with his wife through marriage. Okay, so remember, if you want to know whether husbands are generally taller than their wives, right, we must measure the height of each husband in the couple, and then likewise measure the height of each wife in the couple. Okay, and then we would obtain two samples, right? So one sample containing the heights of all the wives, and then the other sample containing the heights of all the husbands. Okay, so because we've collected the data from married couples, okay, the samples are dependent because each wife, the height of each wife is paired with the height of each husband. Okay, so that's one example of two samples that are dependent. Okay, likewise, if you want to know whether a weight loss program is effective in helping people lose weight, okay, we would randomly select individuals from the population, all right, record their before weights, and then have them participate in the weight loss program, and then record their after weights. Okay, so pause the video and read that on your own if you have to, so that it makes sense for the type of data that we're collecting. Okay, so again, if you want to measure the effectiveness of a program like a weight loss program, okay, you select individuals to participate in the study, okay, and then you make measurements on those individuals before they do the study or the program, okay, and then you have the individuals go through the program, and then after they complete the program, you take measurements on the same individuals. Okay, so in other words, you're going to have two samples of data, right? So one sample is going to contain the before measurements, like the before weights, okay, and then the other sample data will contain the after weights. So once again, what makes the data in these two samples dependent? Okay, so in other words, the before weights are paired with the after weights, okay, based on the individual. Okay, so each before weight is paired with the corresponding after weight, okay, based on that individual. Okay, so the before weights are paired with the after weights based on the individual, making the two samples dependent. Okay, so if you want more information, please see page 418 and section 8.1. Okay, so really quickly, you can see that the book defines independent and dependent samples. Okay, so compare the definitions here with the definitions I gave you in the video. Okay, it's also important to know that when you deal with independent, or rather dependent samples, okay, dependent samples are sometimes called paired samples, right, because the data values are paired in dependent samples, okay, or matched samples. Okay, and you have a diagram of independent samples, right, where the samples are different sizes. Okay, likewise, you have a diagram of dependent samples where each data value in both samples are matched, okay, based on the relationship connecting those individuals. Okay, or, right, if these two samples represent before and then after data, okay, then the relationship connecting the values in the two samples would be that, for example, this would be the before weight of one individual, then likewise this would be the after weight on that same individual. Okay, and likewise for the other data points, right? This would be the before weight on another individual, and then the after weight on that same individual. Okay, so I encourage you to look at example 1. Okay, so it simply asks you to classify each pair of sample as either independent or dependent. So then you would read the description, and then based on the description, determine whether the samples are independent or dependent. Okay, keep in mind that if the sample sizes are different, okay, then the two samples cannot be dependent, because with dependent samples, the sizes of both samples must be the same. However, if you happen to have two independent samples where they both contain the same number of individuals, that does not automatically make the two samples dependent. Okay, so remember, there must be a relationship between the values in one sample, connecting them to the values of the other sample to make them dependent. So once again, right, if you're dealing with independent samples with the same sample size, that does not mean they're automatically dependent. Okay, so I think I've said enough about that. So we're actually going to begin section 8.2. So we're going to start section 8.2, and then in the next video we'll do a couple of examples from the homework. Okay, so section 8.2 begins on page 428 in case you're following along in the ebook. All right, so let's go over some basic information from this section. Okay, on hypothesis tests on two means from independent samples. Okay, so this is the basic setup of the hypothesis tests in this section, okay, including some important notation. Okay, so mu1, okay, so you might remember the symbol mu, the Greek letter mu, represents the mean of a population. Okay, so because we're dealing with two samples, okay, we're going to look at the difference between two means from independent samples, okay? All right, so mu1 is the mean of the first population, and then mu2 is the mean of the second population. Okay, so unless you have all the data for the entire population, you're not going to know the mean of these two populations. Okay, so you're not going to know the values of these. All right, x bar 1 and x bar 2, okay, are the sample means from the first and second samples respectively. So you will have these values, okay, or you can calculate them from the data. All right, so these are the sample means from the two samples. Likewise, S1 and S2 are the sample standard deviations of the first and second samples respectively. So remember, the lowercase letter s represents the standard deviation of a sample. Okay, likewise, x bar represents the mean of a sample, but because we're dealing with two samples, right, the subscript on the symbol tells you which sample it refers to, whether it's the first sample or the second sample. Okay, N1 and N2 are the sample. This should say sample sizes of the first and second samples respectively, so let me just update that really quick. So sample sizes. Okay, so remember the lowercase letter n always represents a sample size, so because we're dealing with two samples, n1 is the size of the first sample, and n2 is the size of the second sample. So the number of individuals that are in each sample. Okay, so in section 8.2, the null hypothesis will look like the following. So H0 is the null hypothesis. Okay, so because we're dealing with the means from two different populations, right? mu1 minus mu2 is the difference between those two means. Okay, and we're going to replace the question mark with either the less than or equal to, greater than or equal to, or equal to symbol, okay, based on the wording given in the problem. So this will be either greater than or equal to, less than or equal to, or equal to 0. Okay, likewise, the alternative hypothesis HA will look like this. Okay, where you replace the question mark with either the less than, greater than, or not equal to symbol. Because in other words, mu1 minus mu2 will either be less than 0, greater than 0, or not equal to 0. All right, and we will still follow the same steps that we did in the previous chapter to do the hypothesis tests in this chapter. Okay, so in step 1, you always state the null and alternative hypotheses using the appropriate symbols. Step 2, determine the level of significance alpha. Okay, and if it's not given, use a significance level of 0.05. Okay, so in other words, the significance level should be given in the problem. All right, step 3, you're going to determine the p-value using Statcrunch. Okay, so if you have a summary of the data, right, you go to the stat menu and select the appropriate function, and then select summary data or summary or with summary. Okay, if you have the raw data, the actual data values, right, you're going to copy the data into Statcrunch first, and then select the appropriate function from the stat menu, and then you're going to select with the data. Okay, step 4, you want to decide whether to reject or fail to reject the null hypothesis based on your p-value. So remember, if your p-value is less than the significance level, you reject the null hypothesis. If it's greater than or equal to the significance level, you do not reject the null hypothesis. And then lastly, in step 5, you state a conclusion based on your results. Okay, so in other words, you're going to start your conclusion with the following phrasing, right? Either there is sufficient evidence to blah, 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 or there is insufficient evidence to and blah, blah, blah. Okay, based on the decision you made in step 4. So in the next video, we'll go over some examples from section 8.2.